Okay, so first part of your guys' homework for this week is pertaining to exponential functions. So the first thing that we're going to review here is what an exponential function is. This is an exponential function right here. How you can tell is because of the x that is in the exponent spot. In this case, the x is not in the exponent spot, so that is not exponential. In this case, the x up here is not in the exponential spot, so that is not. So anytime you have an x up here in the power spot, that is what makes a function an exponential function. Sometimes they can be written with some more numbers involved, and this is kind of how we wrote them initially when we learned them. So in this case, on part B for number 1, all we have is the b to the x power, but they can have a number in the front being multiplied to them or a number after them being added or subtracted. And so long as you have an a variable in the exponent spot, then that's an exponential function. Now, let's just kind of experiment a little bit here. If I were to plug in, make a little table of values here real quick. If I were to plug in 0 for x, I would end up with 1. 3 to the 0 power equals 1. If I were to plug in 1, I would get 3, because 3 to the first power is 3. And if I were to plug in 2, I would get 9. And so what's happening here is every time the y values are increasing by multiples of 3. And that's what makes an exponential function exponential function. It's the fact that it either increases or decreases by multiplying something over and over again. And so that's going to help us understand how to do the next part when we get to number 3 here. But for now, let's talk about number 2. The growth factor is this number right here. It's the number that is being raised to a power. So number 2 there is what's called a growth factor. And that just basically tells that number right there is the number that you're multiplying by over and over again. So back to part B, when from 1 to 3 to 9, that's because every time we're multiplying by 3, the growth factor. Well, in this case, it would be increasing by multiples of 2. That's what's called growth factor. So that kind of segues us into talking about the tables here. You can kind of ignore the x's. It's not that they don't matter. It's just that in case you haven't noticed, every table has the same x values. So because of that, we don't really need to pay attention to it. But what we do need to pay attention to is the x values. So for instance, what's the pattern here for the y's? So I'm going from 3 to 6, and then from 6 to 12, and then from 12 to 24. What's happening every time? Well, we're multiplying by 2. Since we're multiplying by 2 over and over again, that would be the growth factor for an exponential function. And so this one is, I'll put a check next to it to indicate that this function here, this set of data, does represent an exponential function. Let's take a look at the next one here. For this one, the y value goes up by 1, and then it goes up by 3, if you're just thinking of addition. But multiplication, there's definitely nothing happening here. You can't multiply 0 by anything to get 1. And even if you wanted to just ignore that, so I'll just put a question mark here. That's not possible to multiply 0 by something to get 1. And to get from 1 to 4, you'd have to multiply by 4, right? And then to get from here to here, from 4 to 9, you'd have to multiply by something a little bit weird. What would that have to be? It would be 2.5, I think, actually. I just got that by dividing 9 by 4 to see what I'd have to multiply the 4 by. And as you guys can see, that there is no growth factor here. It's not a consistent growth factor. And so this one is not an exponential function. The next one here, to get from here to here, what we could be multiplying by, if you just divide 4 by 16, 4/16, which reduces to a fourth. So if I multiply 16 by 1/4, I'll get 4. Let's see if the same thing holds true here. What if you multiply 4 by 1/4? Cancel, I'm left with 1. So if I multiply 4 by 1/4, that gives me 1. And what happens if I multiply 1 by 1/4? 1 times 1/4. That gives me 1/4, which as a decimal is 0.25. So we do have a consistent multiplication going on here every time we're multiplying by a 4. So that's my growth factor, and this one is in fact a exponential function. So basically, if you do the second y divided by the first, and then the third y divided by the second, and then the fourth y divided by the third, and you keep getting the same number every time, then that's a consistent growth factor that indicates you're dealing with an exponential function. But if you do division and you don't even end up with a consistent outcome there, that's not an exponential. Let's do one more. 6 divided by 3 is 2. So to get from here to here, I would be multiplying by 2. 9 divided by 6, what would that be? That would be 1.5. So as you guys can see, we already do not have a consistent growth factor. Therefore, this one is not an exponential function. So it says here, for each exponential function identified in number 3, identify the growth factor. We already did that. So for the first one here, the growth factor was 2. And for this one here, the growth factor was 4. Okay? And so that's what exponential functions are. That's how they look in tables or as equations, and that's what growth factors are. Part of our discussion when we were talking about exponential functions this year was that sometimes you have a special growth factor called e, and it's not a variable, it's actually a number. It's a number that is approximately equal to 2.71. Okay, and it's called Euler's number. And what's significant about Euler's number is that it's something that is used to model real-life growth where things are constantly growing at an exponential rate. It just works a little bit better. In particular, it's very friendly to use for calculus as well. And so that's why we kind of take time to teach you guys about it, just to kind of give you a brief introduction to it. So Euler's number is 2.71. It's a special base that you can use when talking about exponential functions. That's the answer to number 5. Euler's number is 2.71. And it's just basically a special base that we use when talking about exponential functions, or a special growth factor. You might hear me using the word base to refer to a growth factor. They're kind of the same thing. So, now on here, for numbers 6 through 9, these are all actually 6 through 10, these are all word problems, which we did talk about this year, but for our final and review, I'm not going to focus on them. They're really not that big of a deal. So I'm just going to ignore the word problems. And in fact, on your guys' homework worksheet, you don't even have them on there. So I'm just going to skip ahead here to number 11. So this one here, what we're going to be doing for numbers 11 through 13 is just evaluating exponential functions. So we have, that's 2. For number 11, we have a function, an exponential function that looks like this. And we're being asked for part A to find f of 2. And what that means is we're just going to be plugging in 2 for the exponent. And so when you want to evaluate an exponential function, basically you just do the power first. And after that, you do the multiplication. So 3 times 16 is 48. So the answer to part A there is 48. Let's do part B. For part B, f of 0 would look like this. Now, any number raised to the 0 power is equal to 1. And so the answer for this one is just 3. Let's go ahead and take a look at part C there. Now, the negative exponents are a little bit weird. We've talked about those a while back. First of all, the fact that it's negative makes it become, instead of being 4, it makes it become 1/4. So the negative causes the 4 to go to the denominator, and then once you do, the exponent on the 4 becomes positive at that point. And so now we go ahead and once again we do our exponent. That becomes 1/16. And now when you multiply this 3 times the 16, you can just think of that as 3 over 1 and just do top times top and bottom times bottom. And so we end up with 3/16 as our final. Next few problems are honestly just a little bit repetitive, but I'll do some more in case you want to see some more. So let's go ahead and take a look at number 12. So for number 12, we want to find g of 2 first. Now, in this case, we're squaring the 1/2, which means you do 1/2 times 1/2, right? I'll show my work here on the side if you want. 1/2 squared, that means 1/2 times 1/2, which basically just means 1 over 4. So we end up with 2/3 times 1/4. And then top times top, bottom times bottom gives me 2 over 12, which can be reduced to 1/6 is our final answer there. You do need to reduce if possible. Let's take a look at another one here. Let's do g of negative 2. So we're going to plug in negative 2 there for the x. Now, once again, the negative exponent causes us to do a reciprocal. So instead of being 1 over 2 to the negative 2 power, it becomes 2 over 1 to the positive 2 power. So the negative causes you to flip the fraction over, okay? And then once you do, the exponent is no longer negative. So now we're going to go ahead and square 2 over 1. That's going to end up giving us 4 over 1. And if you multiply straight across, you end up with 8/3. Now we're going to transition into something else. We're going to talk about solving equations at this point. So solving exponential equations requires you to get the left side of your equation and the right side of your equation to have the same base. Now, back when we did this unit, I gave you guys a listed table of values, which, you know, I'll reproduce a little bit of it here for you just to kind of jog your memory. But like I told you that 2 to the 1, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th. I gave you all those answers. Oops. And so if you have your notebook with you, you can just look back at that. It might help you. If you don't have your notebook, you might want to take the time to go ahead and make a quick little table like this for 2s. You can also do it for 3s. And you may be wondering, well, Mr. Bailey, how high up do I have to go? Well, I would say go up to like maybe 5 would be the biggest you'd need to go up to. But anyway, I'm going to stop there. And anyway, what you do is you're going to look at your table and you're going to find which table has both of these numbers in it, 64 and 4. Well, on the table I gave you guys, there was actually 2 tables that would have had that. One would be the 4s, the other would be the 2s. Now, since I have the 2s up here, I'll just work with the 2s. As you can see, 64 can be replaced with 2 to the 6th power, and 4 can be replaced with 2 to the 2nd power. And that's what you want to do. So you're going to change these bases so that they match. So I'm going to replace each of those bases with a base, with a new expression of an exponential expression that has the same base, which in this case is 2. So I'm going to replace 4 with 2 squared, and I'm going to replace 64 with 2 to the 6th power. So that's the first and most important step, is you want to change the bases so that they match. Okay, change these into 2 exponential expressions that have the same base. Sometimes you only need to change one of them. Sometimes you need to change both, like I did. There it is. Anyway, the next thing you're going to do is you're going to put these exponents together, and the way you do that is by multiplying. So that's going to actually end up being 18x now. And now that we have 2 to the 18x power is equal to 2 to the second power, we can kind of just ignore the bases and say, okay, well, if those two sides are equal, that means that 18x must equal 2. This must equal this. And then you just solve by dividing. And you end up with x equals 2 over 18, which reduces to 1/9, the final answer. So your steps are to get the bases to match. Now there's some other things that we're going to keep in mind here as we work, like what about negative exponents and all sorts of stuff. We'll look at a few different scenarios, but let's go ahead and take a look at number 14 here. Now number 14, I want to change 27 and 81 so that they have the same base. And once again, if you took the time to have a table of exponential expressions written out, you would see that both of those can be rewritten to have a base of 3. 27 can be changed into 3 to the third power, and 81 can be changed into 3 to the fourth. Once again, you're going to multiply these exponents here, so you end up with negative 3x and exponent. And I'll get rid of my parentheses now. And then drop off the bases, and you're left with negative 3x equals 4. And then division gives you your final answer of negative 4/3. For the next one here, you guys can see that they already have the same base, 2 and 2. So in that case, we don't need to change them. They already match. So we can just drop the bases off. And what I'm left with then is m minus 1 is equal to m minus 3. And we just solve this equation. Now in this case, something kind of weird happens. I'm going to subtract m on both sides. And by doing that, we actually end up with m's canceling on both sides, and we end up with this weird expression. Negative 1 equals negative 3. Now that's a false statement. Negative 1 is not equal to negative 3, and I didn't solve for m, so that means there's no solution. It just doesn't have an answer to it. Let's take a look at number 16. For number 16, we can rewrite these bases. The 125, that can be rewritten as 5 to the third power, and the 25 can be rewritten as 5 squared. Now, the next step is where this one gets a little bit different. We're going to put these exponents together, but when we do, you got to understand this negative 3b minus 1, that's like a binomial. So when you multiply, you're actually going to distribute this 3 into both parts of that binomial. So you're going to end up with negative 9b minus 3. So you're going to multiply this 3 times both terms of that binomial exponent there. After that, drop your bases off, and you have a nice simple linear equation to solve. Add 3 on both sides. And divide. And we end up with 5 over negative 9. As for number 17, this one's really weird. This one's a little bit different from the other ones. Here's what we're going to do here. We're going to keep this side the same. 3, negative 3, n, right? But I can change 1 into a common base. I can rewrite 1 as a base of 3 if I give it a power of 0. Because any number to the 0 power equals 1. So anytime you have a 1 involved in your equation, just make this 1 match this base and give it a 0 power. Any number to the 0 power equals 1. In this case, these drop off, and I'm left with negative 3n equals 0. If you divide both sides by negative 3, you just get n equals 0. Now, for this one here, the bases already match. So when the bases match already, again, you can just drop those off, right? So now I've got 3a equals 3a. It's kind of weird, right? Divide both sides by 3. You end up with a equals a, and it's kind of like a. If you want to keep going further, you can. You just end up with 0 equals 0. So in this case, the a's go away, kind of like they did up here when we were solving the m's. The m's went away. But for number 15, we got no solution because we got something weird like negative 1 negative 3, which is false, right? But over here, we end up with 0 equals 0. That's actually true. And so what this means is all real numbers. That means that basically these two sides are exactly the same, which honestly you could have noticed that at the very beginning anyway. And since those two sides are the same, it doesn't matter what you plug in for A, you're always going to get the same answer. Okay? Whereas for these ones, no matter what you plug in, you're never going to get those two sides to match. So this is an example of no solution. This is an example of all real numbers. They kind of have something similar happen when you're solving. They both have their variables go away. But in this case, you're left with a false statement. In this case, you're left with a true statement. All right. Now, as for number 19 here, I don't know if I'm going to do all of these problems, but I'll do a couple. It's graphing exponential functions. Okay. So the first thing that we're going to do is I'm going to give you guys some steps on how to graph these. So the first step, marker enlarge. So the first step when you're trying to graph an exponential function, remember this is what they look like. First thing you're going to do when you're trying to graph an exponential function is you're going to graph the horizontal asymptote. I'll abbreviate that HA, the horizontal asymptote. And horizontal asymptote is the line y equals that number. It's y equals. The next thing that you're going to do is you're going to find your Y-intercept. Now, usually to find your Y-intercept, what you do is you plug 0 in for x and solve, and that will work. However, there's a faster way to do the Y-intercept. Faster way is to take the A and add it to the C. And that's your Y-intercept. So, it'll save you a little bit of time if you do that. The reason why that strategy works is because when you plug in 0 for x here, this piece goes away, it just becomes 1. And so when you multiply 1 by the A, you're just left with the A. And so you're just basically left with combining A and C together. So that's why it works. The last thing that we're going to do is we're going to, what else do we do? Let me see. Ways to do it. So what we learned when graphing these earlier was kind of gave you a table to look at. Now they all have a horizontal asymptote, so I'm going to be drawing a horizontal line on each of these to represent the asymptote. Okay, now for both of these problems here, this is for where we want to look at whether the A is positive or whether the A is negative. And we also want to be looking at whether B, the absolute value of B, means, I guess that's kind of unnecessary. We don't need to pay attention to the sign. But we want to make sure that if B is bigger than 1 or if B is a fraction number that's between 1 and 0. Okay, so in the case where A is positive and B is greater than 1, the graph looks like this. Now, if your A is negative, it's like you're taking that picture there and you're flipping it upside down. In the case where B is between 0 and 1 with a positive A, your graph actually goes down, it decreases as we move to the left instead of increases. And then, of course, if you have a negative A, that just flips it over, so it looks more like that. Okay, so there's our three-step process. We're going to graph our horizontal asymptote. It's y equals c, which is represented by this dotted line here. Then we're going to plot a dot on our y-axis for the y-intercept. That is going to be at where a plus c is. And then finally, we're going to use this chart to get a graph. So let's apply these steps and we'll graph number 19 really quick here. So for number 19, the first thing we're going to do is plot our horizontal asymptote, right? And that's going to be at the line y equals c. And in this case, our C value is -2. So I'm going to go down 2, and I'm going to put a horizontal dotted line. Okay. The next thing that we do is we're going to plot our y-intercept. That's the value a plus c. So in this problem, I have a is -2 and c is -2. So if I add those together, I end up with -4. So I'm going to put a dot at -4 on the y-axis. So now I've got the first two steps done. I've got my horizontal asymptote, I have my y-intercept, and now I just get to figure out what shape I'm working with. So we have to look at two things. Is my a positive or is my a negative? Well, my a is negative. So that tells me that I am in this column here on the right. It looks like either the one on the top or the bottom. And then I'm going to look at my b value. It's a half. In that case, a half is between 0 and 1. So since that is the case, we're going to be drawing our graph to look something like that. So I'm going to have kind of a shape like that almost, if you will. Okay? And so that's basically the gist of it. I'll do one more problem like that, and then we'll talk about 23 and 24. Those ones are slightly different than the others. If you want to take a picture of these steps, I am going to erase them, though, for the next problem. Pause the video and take a picture if you want to. Write it down. All right, so for number 20, step 1 is to do your y-intercept, your horizontal asymptote, which is 1. So I'm going to put a horizontal asymptote at 1. Then I'm going to do my y-intercept, which is a plus c, 5 plus 1, which is 6. I have a dot up there. And then since my a is positive and my b is greater than 1, my graph is going to have this shape. Okay, and that's that. Now let's go ahead and talk about these ones here, the bottom two. These are a little bit different. So it's not that different, honestly. If you think about it, E is 2.71, right? So 1 over E is going to be kind of a weird answer. Let's see what that is. That's 1 divided by 2.71. So let me just type that in my calculator. 1 divided by 2.71. And I get 0.36, or 0.37, we'll say. Now, that's pretty much all you need to know to be able to do the problem, because the rest of the steps are the same. So I'll do 23 here. For 23, my horizontal asymptote is -2. So my y-intercept is -5 plus -2, which is -7. Ghetto here and really squeeze those together so it fits out through the screen. And then from there, we're going to determine the shape. Now, my a is negative, and my b, this is why we changed them into decimals. My b is 2.71. So basically, if you have an e right here, that means b is bigger than 1. And that means that my graph would have this kind of a shape. Now, as for this other one over here, horizontal asymptote is 2. Y-intercept is 5 plus 2, which is 7. And 1 over e gives me 0.37, which is less than 1. So I have a positive a value with a b value that's less than 1. And so it won't fit on here unless I erase this stuff. So that would be the shape that looks like this. Okay? And so that's it. So basically, the only thing that's different about these problems is that since we're using the letter E to represent Euler's number, you just need to know that E means that B is bigger than 1. 1 over E means that B is less than 1. So that's graphing exponential functions. All right, we'll move on to part 2, which is talking about logarithms. This week's workload is a little bit bigger than usual because next week, our last week. So I want to kind of get through everything so that you can focus on just your final next week. Let's go ahead and take a look at logarithms. Now there's a lot of problems on here. I am not doing all of these. I'm just going to do the odd problems here for the most part. I might do a few different ones along the way, but for the most part, just going to do like about half. And once you don't have to watch this whole video, you just need to watch the parts that you feel like you need help with. Anyway, so first of all, we want to make sure that you guys know how to solve some log equations, it looks like. Now this thing's a little bit out of order. I'm going to try to go in the same order that we would be going in, that you'll be going in on your test. So let's focus on number 3 first. That's going to be like your number 15. Okay, so it says find the inverse of the function. Now the reason that we talked about this is you can find the inverse of any function you want to, but the reason we're talking about it now with logs is because what a logarithm is basically is it's just an inverse of an exponential function, so they're kind of like opposites of each other. So the steps for finding an inverse are as follows. The first thing is you're going to replace f of x with y. Okay, so I'm going to take number 3 here, and I'm just going to replace the f of x with y. The reason we do that is just because the f of x is a big clunky symbol, and it makes doing math kind of awkward, so we get it out of the way. It's not really technically even a mathematical move, it's just a cosmetic move, making it look simpler. The next thing we're going to do, and this is an important step, is you're going to switch the x and y. That is actually the inverse step there. By switching the x and the y, we have just created an inverse function. But in number 3 is the hard step. When you have a function, you always need to have y by itself. So step 3 is to get y by itself. Okay, so that's where your guys' knowledge of basic algebra, unit 1 stuff that we talked about earlier this year and also last year in Algebra 1 comes into play. So I need to get y by itself. There's a variety of ways you guys can do it. First of all, I don't like fractions, so I'm going to multiply everything by 4. Okay, and by doing that, we get 4x here, 16 here, negative 16 actually, and then these 4's cancel. That's the whole reason I did it, is so that we now no longer have the fraction there. The next thing I would do is I would add this 16 to both sides, and you can't really add the 16 to the 4x because they're not like terms, so we'll just put them next to each other. And then the last thing we're going to do is divide both sides by 7. And that ends step 3. Now there's 2 ways you could write this. You could write it like that. You could say it's 4x plus 16 over 7. Or you could also say it's 4 over 7x plus 16 over 7. In other words, you could split the top up into 2 separate fractions. And that would be the inverse of f. And the way that we write that is that instead of putting y now, we'll put f with a little negative 1 there. And all that means is that this function here is the inverse of this function here. They have the same letter, but this one is a little negative 1, indicating that these are opposite functions. And once again, we may leave them just like this, by the way. This would have been an acceptable answer as well. Okay. All right. So that's it for that one. I'm not going to do number 4. Your guys' next question is rewriting equations in exponential form or logarithmic form. So I'm going to go back to my notes here and I'll do one like that. Here it is. So numbers 9 through 12 will answer that. So this is for numbers 16 and 17. I think those match. So, what you need to know here is that if you have an exponential expression that looks like this, that's good enough. I'm going to make a little difference here in how I write it. I feel like it's less confusing if I write it this way. It's technically fine to leave it that way. I like writing like this. If you have an exponential function like this, you can rewrite that in log form, which is where the base for a log, you write it as a little subscript there. So the b goes down there by the word log. And then the x and the y switch places. So in the exponential function up there, the x is the input, the y is the output. But for the log, the y is the input and the x is the output. And so that's how you rewrite. So I think I'll start off with 17, and then I'll go back and do 16 after that. So let's do here. So if I wanted to rewrite number 17 or 11 here as a log, I would write log, and I'd put the 7 down here as a little subscript. That's its base. And then the input and the output switch places. So the 343 goes here, and the 3 goes here. Okay. Now we can work backwards as well. When you're writing this as an exponential function, we don't have the word log anymore, so we get rid of that. The 17, the little subscript there, that represents the base of our exponential function, and the input and output get switched. So the 2 goes in the input, and the 289 goes on the output. Okay, so that's rewriting exponential functions and log functions in terms of. All right, next question for you guys on yours is numbers 18 through 21, which is basically going to be just applying some basic log properties. So let's take a look at similar types of problems here. So this is for your guys' numbers 18 through 21. All right. So we have some basic log properties that we talked about a little while ago. I'll write them down for you really quick here on the side. We know that if you have a log with a base of a, if there's a 1 here, then the answer is 0. Whereas if you have a log with an a here, and an a here, the answer is 1. And what's another one of our properties? If you have a log with a base of a, and part of the argument, this part of the log is called an argument, by the way, and the argument is a to the x. So if this base matches the base of the exponential function inside of it, then basically it's kind of like the log a cancels the a, and you're just left with the x. Okay. Next, we had another property which is kind of similar to that. See, what this one's kind of like is like it's like you're plugging an exponential function into a log function, so they cancel each other out, and you're just left with the x, right? Well, the next problem is kind of like that. It's where you have an exponential function and you plug a log function in. And the same effect happens. Basically, the base of the exponential function cancels the log base a, and you're just left with x. Okay, but I'm going to take off the cross-off mark because I don't think that's helpful. Just put x here. Another thing that we want to be aware of for these particular problems is that the argument of a log, that's the part that is inside the log. All of these things here are what's called the argument of the log. The argument of the log always has to be greater than 0. It can't equal 0, and it can't be less than 0. If it is, there's no solution. So those are our basic log properties you want to keep in mind. We'll talk about other special properties pertaining to exponents as we kind of plow through the problems here. So let's go ahead and talk about a couple of these. So a lot of times what you're going to want to do is to get the bases to match. So the base of this log is 5. Now I want the argument to have a base of 5 as well. So I'm going to put log base 5, and I'm going to change that 25 to be 5 squared. The reason I'm doing that is so that I can apply this property here, which tells me that these cancel, and so the answer is 2. So log base 5 of 25 is 2. Another way you can solve this instead of using the log properties is you can kind of just try to think of this as an exponential problem. In other words, this equals some unknown number, right? But if you think of this as an exponential problem, then basically this is 5 to that unknown power equals 25. And so 5 to what power gives you 25? And the answer is 2. So you can think of it as an exponential function, or you can just use these log properties. Personally, I think the log properties are faster, but that's because I've memorized them. If you guys haven't memorized them, sometimes it can be a little bit harder. Here's another one here. Log base 6 of 216. Basically, that means 6 raised to what power is 216? Or we can get the bases to match, right? That's going to end up being 6 to the 3rd, I believe. These cancel, and I'm left with 3. Another thing that you may have to deal with on these particular problems is fractions. So, first of all, I'm going to rewrite that 1/8 as just an 8, which I'm allowed to do if I make it a negative 1 power, right? Because a negative 1 power is what makes it a fraction in the first place. So if I just change this to 8 to the negative 1, then I'm good to go. I'm going to change how I wrote it a little bit. I like parentheses myself. Entirely necessary there. All right, the next thing we're going to do is, like the other two, we're going to get the bases to match. It turns out you can change 8 to be 2 to the 3rd power, right? And then, like when we talked about exponents, we can just put those together. Those cancel. We're left with negative 3. Okay. You would do something similar here on number 16, which I'm going to skip for now. Let's go ahead and jump on up to number 17. For number 17, actually, I think I'll do 18 first. A little bit easier. So the bases already match, but the issue is that we have that cube root there, right? But it turns out there's a way you can rewrite cube roots as an exponent instead. I can change that to be 5 to the power of 1/3. So that's 5 to the 1/3 power. A cube root is the same thing as a 1/3 power. So if we just cross those off now, we see that our answer is 1/3. Whereas over here for the number 17, square root has a 2 here, even though they don't write it. And so what this is really is this is log 10 to the half. Now you guys may be noticing that something's missing here. And we talked about that back in our days of logs. And this is what's called a common log when you don't have the base here. And when the base isn't written, that means the base is 10. So the bases here do match, and these just cross off, and I'm left with let's go ahead and take a look at some more here. For number 19, ln is what's called the natural log. The natural log, that's the same thing as saying log with a base of e. So if it helps you, you can just change ln into log base e. And then you see it just basically follows these rules here. So this one cancels here, and we're left with 5. Here's another one, log 1. So remember, if they don't put the base there, that means the base is 10. So if it helps you to write it, go ahead. Now in this case, we have a rule for this already. Anytime there's a 1 here, anytime your argument is a 1, the answer is 0. So using that rule up there, we can get a nice simple answer pretty quickly. Let's go ahead and look at the next one here. Number 21. This one, we don't have a rule for that. There's nowhere where the argument equals 0. There's no way to get this number to match this number in bases. You can't ever write 0 as 2 to a power of any kind. So some of you guys might be thinking, well, what about 2 to the 0? Well, that doesn't work, because remember, a 0 power doesn't make something equal 0, it makes it equal 1. That's not going to work. The issue here is that there's no solution, and it's because the argument has to be greater than 0. In this case, my argument is 0. It's not greater than 0, it actually equals 0. That's not allowed. So this thing has no solution. Take a look at number 22. Number 22. Anytime the base matches the arguments, we have this situation here, which is our second log rule. That basically just tells us the answer. In this case, there's no solution because, once again, our argument is less than 0, so that's a no solution problem. And once again, we have an E, so it might help you to rewrite that ln there as a log base E, in which case we see that we're looking at this rule here, where these two pieces cancel and you're just left with is your final. Okay, so those are some of your basic log properties. All right, so our next question we're going to look at here is your guys' number 22, talking about the change of base formula. So let me bring up an example like that. So for me, I'm going to be doing these ones for change of base. So the way that change of base works basically is a lot of times we don't, like, you can't figure this out. There's no way to do that by hand. We wouldn't be able to use our properties to get this answer. And unfortunately, we couldn't even really use our calculators because our calculators are all in base 10 or base E. So what we want to do is we want to change it to a base of 10 so we can use our calculator. And so to do that, we're going to use the change of base formula. And it looks like this. So if you have a log with any random base A, and let B be the argument, you can rewrite that as a log with a base of 10 instead. Just write it twice, 2 different ways there. And you're going to do log base 10 of B divided by log base 10 of A. And so this is what we would type into our calculator. We would find the log base 10 of the B, and we would divide that by the log base 10 of the A. So in this case, this is my B, and 4 is the A. So this particular expression here for number 25, we would write this as log base 10 of 4.7 over log base 10 of 4. And this is what I'm going to type into my calculator. So let me bring up my calculator here real quick. Okay, so I'm going to push 4.7 log, which is base 10. You guys can see it says here on the calculator log of 4.7. That's what I typed in. And then this is the answer to that. And then we're going to push divided by, and then it's going to be 4 log. So we have log 4.7 divided by log 4. And then the final thing we have to do is push equals. So it gives us the final answer there. And so it's 1.11. And there you have it. Okay. Now, if you wanted to, you could check your answer. You don't have to do this, but just to kind of show you how it all kind of ties together. So we just used the change of base then to prove that this thing is 1.11, right? Well, if I change this into exponential form like we did on one of our first problems we looked at, we would rewrite that as 4 to the 1.11 power is equal to 4.7. Okay, and so that means if you raise 4 to the 1.11 power, it should be pretty close to 7, or 4.7, I mean. So let's see if that works. This is just a way to check your answer. You do not have to do this. But 4 to the power of 1.11 should be about 4.7. And as you see, we get 4.65, which if you round up to the 10th, would be 4.7. So we have a good estimate of what the answer is. And that's the change of base. All right. Let's go ahead and see what your guys' next problem is. So we talked about 22. Let's talk about numbers, I think what I'm going to do is I'm going to wait on numbers 23 and 24. I'm going to jump ahead to numbers 25 and 26 just because it's a little bit easier, and then we'll work backwards to 23 and 24. So let's talk about how to do all of these here. Okay. The first thing we got to know is we need to know some more log properties. So we have one log property that looks like this, where if you have log, I'll put him here, plus another log with the same base of a, but a different argument, let's say it's n, you could put those together as one logarithm with a base of a, and these two arguments being multiplied together. Okay, so that's one of the new log rules we want to be aware of. Another log rule is kind of the same. It's where you would be subtracting these instead. Now, when you're subtracting them, you could write that as one log with the same base of a, where the two arguments are being divided. Now, you got to be careful with this one because the order matters. Whichever one comes first, like the m is first on the left and the n is on the right, or in other words, the log with the base a of n has the negative in front of it, right? The one that's the positive log has the argument go on the top, so the m goes on top, and the log that's negative, its argument is the one that goes on the bottom whenever you set it up. The last thing is if you ever have a log that's being multiplied by something, like let's say times, right? You could rewrite that as the same exact expression, really, but instead of putting the u as a multiplier in the front, you make that u become a power of the argument. So these are three additional properties that we're going to be using to solve your numbers 23 through 26, I think it was. But for me, first of all, I'm going to start with helping you guys out with your numbers 25 through 26. Okay? And what those ones are basically is they want you to condense. They want you to put the logarithms together into a single logarithm. They don't want to have three separate logs. They want all of them put together into one log. All right. Let me start off with an easier one here. Let's start off with 32 first. Okay. Well, taking a look at this piece only, I can apply this rule down here. This rule down here, the third one, says that when you have your log being multiplied by something, you can make it become a power of the argument. So I'm going to rewrite this log on number 32 as log base 5 of x to the power of 18. Okay, so that would be that one. And we could do the same thing for the second log here. I can rewrite that as log base 5 of y to the power of 6. So there's that. But I still don't have just one logarithm. I still have two logs. So I need to put those together. As you can see, they're being added. So that makes us think of this rule up here. When you have two logs being added, you can multiply the arguments together and make it one log. So we could put this together in the following fashion. And now I have one logarithm. So notice the order I went in. I first applied rule 3, where I took the number in the front and made it a power. And then I applied rule 1. Okay, let's do one kind of similar to that. All right, let's take a look at number 33. So first of all, we're going to start by applying rule 3 again, right? So I'm going to take this 2 in the front, and I'm going to make that a power on the 10. Okay, now since we have numbers here instead of just letters, technically you could do 10 to the second power and change that into 100 if you wanted to. But I think we probably won't, because as you can see, like this one here says 7 to the 4th. So if you're going to do this one, you would want to do this one also. But this is a huge number. If you guys want to try it, give it a shot. 7 to the 4th power is pretty big. And usually, since the numbers are so big, the multiple choices that you guys have to choose from is just going to leave them just as numbers like that. So we'll leave it like this. But anyway, so that takes care of rule 3. Now we're going to apply another rule to put these two logs together into one. And that's the rule 2 down here where we have minus. So when they're being subtracted, the first log's argument goes on the top, the second log's argument goes on the bottom. So it would look like this: log base 5 of 10 squared over 7 to the 4th. And that's that. Okay. Let's do another one. Slightly different variation here. I'm going to skip number 34. 34 is just kind of repetitious, so I'm not going to do that one. But I will look at number 31. 31 is kind of weird. You see we have these weird fractions here. What we're going to do is we're going to rewrite this a little bit. Instead of writing it like this is not a log rule. This is just a basic math rule. I'm going to write this as, instead of log 2 of 3 being divided by 2, I'm going to write it as log 2 of 3 being multiplied by a half. And that really is the same thing. I mean, for instance, if you took 10, right, and you multiplied it by a half, that's 5, right? Well, that's the same thing as 10 divided by 2. So this and this are the same thing, right? 10 divided by 2 is the same as 10 times a half. Well, we're doing a similar thing up here on this problem. We are going to just say, okay, well, log divided by 2 here is just going to be half times the log. Now, why am I doing this? Well, because now this fits one of our properties. I don't have anything over here where I have a log being divided by something and I do something bottom something, right? But I do have a log that's being multiplied by something. So by changing this log over 2 into log times a half, now I can apply rule 3 and make this become a power of the 3. Okay, so getting a little bit ahead of myself, but that's why I did it. So let's go ahead and do that with the other ones as well that are there. So it's going to be plus, and I'm going to do the same thing with this log. I'm going to write it as a half times log base 2 of 7, then plus another one. And now that I've rewritten those like that, I'm going to apply rule 3, which is where the thing that's in the front, the multiplier, goes to the top as an exponent on the argument. So it's going to be log base 2 of 3 to the half power plus log base 2 of 7 to the half power log base 2 of 11 to the half. And now you'll notice that we have 3 logs here. Now none of our rules have 3 logs, but whether it's 3 or 2, it doesn't really matter. We'll just do 2 at a time. So first of all, let's put these ones together here. So we'll do 2, these 2 first. So addition becomes multiplication, right? So I'm going to put this together as log base 2, 3 to the half, times 7 to the half, right? But we still have this guy. So now I've got 2 logs again. I put these, we had 3 logs, but by putting 2 of them together, now I have 2 logs. And now I can put those 2 together using the same rule, rule number 1. So I could take this argument, 3 half, 7 half, and multiply it by 11 half. So we end up with now just one logarithm. Now, even though we would like to be done with this problem by now, we have a little bit more work to do here. Real quick. Okay, so a half power, in case you guys forgot, is a square root. So what this really is then is this is log base 2 of the square root of 3 times the square root of 7 times the square root of 11. And since these are all the same kind of square root, we can really just put them all underneath of one root here and write it like that's a property that is about square roots. So there's our final answer. So when you have these little denominators, first thing is that they become fractions of a half in the front, right? And then they become powers. And after they become powers, they become square roots. And if you have a bunch of them that are square roots, you just put them together under one root. Okay. And the only two log properties that we actually ended up using were this one and this one, log 3, or rules 1 and 3 here. But all the other rules were rules about square roots and powers and multiplication and things like that. So had a few things involved there. All right. So that's for numbers 25 to 26. Now, on your guys' worksheet, you also have 23 and 24. So let's talk about 23 and 24 a little bit. 23 and 24 on your guys' worksheet is about expanding. So it's the opposite. So basically, instead of putting them together into one logarithm now, we're going to break them apart into multiple logarithms. Okay, so let's go ahead and get started with that. So first of all, I think this would be a nice time to pick up right here. So the first thing we're going to do is I want to split that up. So in order to split it up, I'm going to break this square root apart into 3 separate square roots, just like that. Right? And then now I have one logarithm here, and in that logarithm, the argument has 3 things that are being multiplied together: the square root of 10, the square root of 11, and the square root of 3. So according to my rules over here, if I have one logarithm with 2 things being multiplied together, I can split that up into 2 separate logs. That. So it's going to be log base 4 of the square root of 10 plus log base 4 of the square root of 11 plus log base 4 of the square root of 3. So now we've got that, but we're going to keep going here a little bit. So the next thing is that we talked a lot about how the square root, you can rewrite that as a power, right? So all we're doing is the exact opposite of the last problem we had. So instead of the square root of 10, I'm going to say it's 10 to the half power. And we're going to continue that for the 11. It's going to be 11 to the half power. And then it's going to be 3 to the half power. Oops. And since we have a half power, we're going to take those powers now. When you have a logarithm whose argument has a power on it, that power can be rewritten as a multiplier of your logarithm in the front. So instead of having it as a power, we write it as a multiplier in the front. So I'm going to be rewriting these 3 logs as 1/2 times the log plus 1/2 times log base 4 of 11 plus 1/2 log base 4 of 3. And then as our final step, multiplying something by a half is the same as dividing it by 2. So we'll write it like this: log base 4 of 10, 2 plus log base 4 of 11 over 2 plus log base 4 of 3 over 2. And now we're finally done. So it's the same exact problem. It's just, as we did earlier, it's just that we're working backwards. We're expanding instead of condensing. All right. I could probably do another one. Let's see if there's another one on here that might have some elements. Let's take a look at this one. Now, before I begin applying my log rules, I don't like how my argument has an extra power up here. So what I'm going to do instead is I'm going to, and you guys should do the same. So if you see one of your logarithms and the arguments have powers being raised to powers, what I would do is I would just apply one of our properties about exponents that says that, let me zoom in here a little bit actually, some better space. I'm going to use one of our properties about logs or exponents that says that you can just distribute this power in like that. So it's going to end up being this instead. Oops. There we go. So if you see anywhere where your argument has a power out here, I would go ahead and distribute it in before you go any further. But anyway, once you've done that, now we can start applying our rules. So I've got one logarithm with two things being multiplied, right? And when two things are being multiplied, those two things can be rewritten as two separate logs that are being added, right? So I can write this as log base 9 of x squared plus log base 9 of y to the 10th. And then finally, we can apply the reverse of rule 3. The reverse of rule 3 says that if you have a power on your argument, you can move it to the front as a multiplier. So we can write it like and there we go. I'll do one more that's kind of like that. Erase this. And I might even change it up a little bit. I'm going to slightly change this problem just because I want something a little bit different. I will use some of it though. Some writing space. All right, so I'm going to use this, but I'm going to rewrite it a little bit as, let's say I want to solve log base 7 of z to the 5th over the cube root. I want to include one with fractions, so I want to ignore that one. So let's pretend we're doing this one instead. Make some more writing space for myself here. Okay. So how would we solve this problem? Well, first of all, I would be applying rule 2. I have a fraction, right? And so when you have two logs that are being divided, m over n, you could write that as two separate logs that are being subtracted. So I would write log base 7 of z to the 5th power minus log base 7 of the cube root of x. Okay. Now, we don't like these cube roots, right? So what we do is we're going to rewrite that as a 1/3 power. Same thing as a cube root, just written as an exponent instead. And then we're going to apply rule 3, where we're going to take our exponents and move them to the front. So that's going to look like this. And then finally, I don't think, even though this is a fine answer, I'm pretty sure that on my software, they're not going to write it as 1/3 times log 7. I think they're, oops, erased a little bit more than I wanted it to. Back up a little bit. Wow. Oh well, I guess I screwed that up. Anyway, I'll just kind of clear off the whole board here. So we left off with this. This is where we were. Okay, so that's where we left off before I moved up there. But anyway, I'm pretty sure they're not going to leave it as 1/3 times log base 7. What they're going to do is they're just going to take that 1/3 times log, and they're going to do log divided by 3 instead. Okay, and so that would be the final answer there. So we talked about expanding and contracting using the 3 additional log rules that we just talked about. Go ahead and take a look at your next set. So we did 23, 4, 5, and 6. Now it's number 27 is asking us to identify the domain. So let me see if I can find one like that. Here we go. Number 35. So for you guys, this is your number 27 on your worksheet. All right. Well, as we talked about earlier, what is domain? Domain is basically all possible values of x. So the domain is basically any number that you're allowed to plug in for x. Now, for a lot of functions, it doesn't matter. You can plug in anything you want to. In that case, the domain's all real numbers. But when it comes to things like logarithms, rational functions, or square roots, there's actually some things you're not allowed to plug in for x. And so logarithms have a limitation. Here's the limitation. We talked about how earlier the arguments of a logarithm has to be greater than 0. And so my argument in this case is 3x minus 1. And therefore, if I solve for x, I can find my domain. So what this means is that x can be anything greater than 1/3. Okay? Anything, but if you were to plug in any number that's less than 1/3 for x, like let's say you plugged in a 1/4 or a -1/2 or a -2, anything that's less than 1/3, if you try plugging that in, that's going to make your argument end up being negative, and the logarithm won't like that. So, how do you find the domain? You set the argument greater than 0 and solve for x. Pretty straightforward. Now, there is a little bit of a difference, though, here when you're talking about some problems. So let's take a look at this one. So for this one, the argument has to be greater than 0, right? So we minus 12. And we divide by -3. Now, something happens here, though. When you divide by a negative number, multiplying or dividing an inequality by a negative number has an effect on the inequality. It causes it to reverse. So notice the arrows are opposite directions there. Anytime you multiply or divide by a negative, so since I divided by -3, this number, the 12, does not matter. It doesn't matter if it's positive or negative. What matters is if the number you're dividing by is negative. And since that's negative, it causes the inequality to reverse. So now what this is telling us is that x has to be a number that is less than 4. So for this logarithm here, you would only be allowed to plug in numbers that are less than 4. And that's what we mean by domain. So let's go ahead and take a look at you guys' next question. That was 27. So now we're going to talk about solving. So that's numbers 28 through quite a few there, 28 through 34. There's a lot to talk about with solving. We have basic. I'll call this a basic equation. The reason it's basic is because there's just a variable for the argument, and that's it. Whereas this one may be a little bit different because now the argument has more in it. It's not just a variable, but it's got more stuff to it. We have other types of logarithm equations where you have numbers outside the log as well as in your argument. So we have outside numbers. And then this one is another type of question as well, because in this particular case you have logs on both sides of the equation. Notice that we don't have that in these other ones. So you guys have a lot of different things to look at here, and you're going to find that also 32, 33, and 34, well, not so much 34, but 32 and 33, these ones they have more than one log, but they're on the same side. How do you deal with that? That's another situation you need to be aware of. So lots of different equations. And number 34 is how do you deal with ln. So I'm just going to go through solving a whole bunch of different types of equations. And after you guys watch it, you can come back and try to figure out how to do each one of these matching over with you. So let's go ahead and start off with number 37 here. I'm going to zoom in and try to make some writing space for myself here real quick. Okay. So when you have a problem like this, what you want to do is a basic logarithm is the key step, and you're pretty much going to be doing this on almost every problem. Number 43 is an exception, but on every other log problem, you're going to be doing this at some point, is you're going to change it to an exponential expression. So we're going to change it to 7 to the power of 0 equals n. And then after that, you just simplify or solve. So in this case, anything to the 0 power is 1. And so what that means is that n has to equal 1. Okay, and that's it. It's that simple, the basic one. And but that main move there where you change it to exponential form, that's something you're going to do on every problem. Let's go ahead and take a look at number 39. Now number 39 is similar. We're going to change it to exponential form. So it's going to be 8 to the power of 3 equals that. Now, sometimes they want you to actually figure out what the power like that is. Like, what is 8 to the third? Actually get a calculator out and figure it out. You could do that. It's not necessary, though. You could really just leave it like this, just minus the 8 on both sides. And so you end up with 8 to the third minus 8. And then divide both sides by 3. So technically, instead of actually calculating what 8 to the third is, you can just write this really weird looking answer, and that's fine. Or you can go through the process of actually figuring it out. I don't know what your multiple choice look like, so if you don't see that, then maybe go ahead and do it anyway. Do 8 to the third power, 512, subtract 8. So that's 504 divided by 3, 168. So if you wanted to simplify this, you get 168 as a final answer. All right, so we did a basic type. We did another type where it's still basic in its structure, but the argument is more than just a letter. Like up here it was just n, but here it's 8. Let's take a look at another one. What about when it's the same, like this question here is exactly like 39. It's just that there's two differences. And it's the 5 out here and this -3. We have outside numbers. So when you have outside numbers, what you do is you get rid of them. So the first thing we're going to do is we're going to add 3 on both sides. So that 3 is gone. And this goes away too, but we have to put something there, so we'll put 0. And then we also, at this point, you're going to divide both sides by 5. Make a little writing space for myself. Okay, so at this point now I'm going to divide both sides by 5. And in this case, 0 divided by 5 doesn't really even matter. So after you get rid of the outside numbers, in this case by adding 3 and dividing 5, it's just like number 39. So we're going to change it to exponential form. It's going to be 2 to the power of 0 equals my argument. Two to the power of 0 is 1, right? Get that out nice and simple. Add the 2, and from here you just do basic algebra. 2 and divide by 7. And we end up with 3/7. Okay, so we've dealt with 3 types of questions so far. We've dealt with the basic one, just change it to exponential form and simplify. we've solved ones where you have numbers inside the argument. Just change it to exponential form and solve the equation and results. We've also looked at ones that have outside numbers. So for those, you get rid of the outside numbers first. Now, okay, so our next type of log equation we're going to solve is the one where you have a logarithm on both sides. If you have just one log on this side and one log on this side, we can just kind of get rid of the log because that's the same. So if we just take it off both sides, then it's not going to change the balance of the equation, right? And so from there, you're left with a simple equation that you need to solve. I'll go ahead and just solve it from here. And if I add 8 on both sides, I end up with m equals 11. Now, for these ones, you might want to make a little star next to them and write a note. It's important to check your answer. Remember, logarithms have domain restrictions. Now, for the other problems we've looked at so far, they'll never give you a false answer. But for this one, you could actually end up getting a false answer, an answer that doesn't actually work. Okay, so it's important that you check your answer. And how do you check your answer? Well, you check your answer by just taking your answer that you got for the variable, which is 11, and you plug it in. So if I plug in 11 here, I'm going to get 44 plus 3, which is 47. And that's okay. If I plug in 11 here, I get 55, take away 8, which is also 47, so we're good to go. We have log base 6 of 47 equals log base 6 of 47. Here's where an issue would come up, is if this answer, when I plugged it in, it'll still make the sides equal no matter what. But the problem is what if we got negative 47? If we got negative 47, that's when we would cross this off and we would say, oh, well, that's no solution. But it doesn't do that. So in this case, m equals 11 is our answer. But for these ones, you have to check your answer because, like I said, you could end up with a false answer, an extraneous solution, an answer that's outside the domain. That wouldn't happen with the first 3 that we looked at, but it can happen here. It can also happen in other circumstances as well, which maybe we'll look at in a second. All right, let's go ahead and feel like there's probably more. So more types of log equations to solve. I put them up here at number 1 and 2. Don't ask why, just being goofy. But let's go ahead and take a look at 1 and 2. I'll go ahead and do both of those actually. Make some writing space for myself first. Okay. So you'll notice on this one, there are logs on both sides of the equation, but it's a little bit different because for this one, there's 2 logs on this side and 1 log over here. Well, we don't want more than 1 log on each side. So what we want to do is we want to somehow put these 2 logs together into 1, and we have a property for that, right? We got through talking about that a little bit earlier. When you have 2 logs that are being added, you can put them together as 1 logarithm if you are going to multiply their 2 arguments, x minus 7 and 5. Okay. Now I have 1 log on both sides, and so from here on out, the problem is pretty much like the last one. Drop the log off both sides. We're going to go ahead and distribute this in, and we're going to get 5x minus 35 equals 39, and the rest is algebra. Dividing both sides by 5, I would get x equals 74/5, and that's approximately equal to, got a calculator out, 1.4-ish. That ain't right. Let me back up. So 1.4 point something. So it's 14, basically. It's pretty close to 14. So the question is, this is one of those problems where we have a log on both sides, right? So we have to check our answer. Does that work? Well, if you plug in 14 here, Are you going to end up with 0? No. Are you going to end up with a negative? No. So this is a good answer. We're going to keep that answer. All right. Let's go ahead and do number 2. Number 2 is different in 2 ways. Once again, let me make some writing space for myself here. Okay. So, like the last problem, we have 2 logs on this one side over here, and we want to put them together as 1. But since it is since it's minus, the way we're going to put them together is as a fraction. So it's going to be negative 3x over 6. Now, another way that this problem is different, unlike the last one, there is not a log on both sides. So the way we're going to solve it is different. You can't just cross the log off. So remember, this is more like the first 3 problems that we solved. When you have only a log on one side, the strategy is to change it into exponential form. So it's going to be 7 to the power of 1 equals negative 3x over 6. Now 7 to the 1 power, that's just 7. So here's my equation so far, right? And I want to solve for x. So anytime you have a fraction, you're going to multiply everything by the denominator. So I'll multiply everything by 6. My denominator cancels. And then I'm going to divide everything by negative 3. And what do I end up with there? I end up with negative 1 or negative 14. And I don't need to check my answer on this one. You only need to check your answer for the ones that end up giving you logs on both sides. Okay. All right, so that does it for solving our next topic that we're going to look at with you guys. But before I do that, I actually just realized that I haven't talked yet about how to solve an equation with an ln in it. So let me make up a quick ln equation really quick so that we can show you guys how to do one of those, because it is on your guys's. You do have one on your worksheet you're working on this week. All right. So let's just say that I had a 5 ln of x plus 2 equals 10. Okay. So in this case, we want to get rid of the outside numbers first, right? By both sides by 5. And now this is one of the ones where you only have a log on one side. So the strategy is to change this into exponential form. But to do that, remember that ln is basically log base e, right? So if I change this into exponential form, it's going to be e to the power of 2 equals x. And if you just minus the 2 on both sides, you'll have your answer. So in this case, x would be e squared minus 2. You just leave it like that. You can get a calculator out and do e squared, 2.71 to the second power. It's going to be something like, a little bit less than 9. So if you take 2 away from it, it'll be a little bit less than 7. But in any event, there we have it. We're going to leave our answer like that. So that does it for solving. So the last thing that we're going to look at now is graphing. On your guys' homework, that would be numbers 35 and 36. So for numbers 35 and 36. So write that at the top there real quick. This is for homework problems numbers 35 through 36. Okay, so how do you graph a logarithmic function? All right, well, the first thing that we're going to do is we're going to find the domain. Okay, now the domain is found by doing the argument greater than 0, right? And then you solve. Solve for x, okay? Now, what that gives you is it tells you where your vertical asymptote is going to be. So whatever answer you got here, that's where your vertical asymptote is going to be. It's like if x can only be a certain number of things, like if x has, let's say for instance, x has to be greater than 2, right? Well, if x has to be greater than 2, then when we graph this thing, there's going to be an imaginary line at 2 that our graph cannot pass, okay? The third thing that we're going to do is, oops, we're going to pick some numbers from our domain. This should say x's here. That's kind of an ugly rewrite that. So we're going to pick some x's from our domain, and we're going to find y. So we're going to put an x here, y here, and we're just going to pick some numbers to plug in to our domain there. Okay. The fourth step is plot and graph. So we have 4 steps there we're going to follow to get these things graphed. Now, step 3 is where a lot of the work comes into play. Finding the y value is actually a little bit of, we have a little bit of calculation to do. You'll probably need your calculators to get these answers. So that's where most of the work is. Now, as for the plotting and graphing, it's important to understand your log function can look like this. I'll draw a little arrow here. Log functions, regardless of which one we're going to be working with, they always have a vertical. They always have a vertical asymptote, so I'm going to draw a little vertical line on all of these. Now, they can go up like that, or they can go down like that, or they can go in the opposite direction as well. Okay, so those are the ways that logarithmic functions work. So I'll review the steps one more time, then we'll start doing some problems here. So step 1, find the domain, set the argument greater than 0 and solve for x. That tells you where your vertical asymptote is going to be, that little dotted line. And then we're going to pick some x's out of the domain. So like if x has to be greater than 2, I'm going to pick some numbers greater than 2. I'm going to plug them into my equation. I'm going to solve for y. After that, we're going to just plot our dots, and our graph will look like one of these 4 things. Done. So I am going to delete these steps at this point, so if you need to take a picture, go ahead. But let's go ahead and jump into number 1 here. So for number 1, number, I guess 45, I should say. We're going to take our argument. We're going to make it greater than 0. We're going to solve for x. That means that x has to be greater than -5, which means that my vertical asymptote is going to be at x equals -5. So I'm going to have an invisible boundary at -5 on my graph. Now the third thing I'm going to do is I'm going to pick some numbers for x. Now those numbers for x that we pick have to be greater than -5. So let's pick a number greater than -5. How about, now a lot of you guys might be thinking -4. That's fine, you could do that. Now the next number you pick, some of you guys might be thinking -3, which would be totally fine. However, my advice to you guys is that when you pick these x values, pick the x values so that they're kind of far apart from each other. So Let's pick another number for x that's really far away from -4. Like, let's go ahead and say I'm going to plug in, how about 10? Okay. Now, the reason for that is because log functions grow really, really slowly. So if you pick two numbers that are too close together, you're barely going to be able to tell the y's apart, and it's going to make it look like it's a flat line, and it's not. So if you just give it a little bit distance, you'll see that it actually has grown. Okay, so now we're ready to start calculating the y values. So what we're going to do is we're going to be plugging in these x's so we can find the y's. And this is, like I said, where most of our work ends up happening. So let's take this and let's go ahead and plug in the first one there. -3 log 3 -4 plus 5 minus 1. So following our order of operations, of course, you simplify the inside of the parentheses first. Now this is a really cool situation. Our log properties can answer that one for us. Now that's not usually going to happen. Usually we end up with something that we're going to have to use our calculators for. But in this case, we actually end up with something here that we have a log property for. Anytime the argument is 1, the answer is 0. So log base 3 of 1 equals 0. And so -3 times 0 is 0. Take away 1 is -1. So that one's pretty straightforward. It's -1. The next one probably won't be as friendly, so you'll see how to deal with those. Go ahead and plug in 10 now. So we have -3 log base 3 of 10 plus 5 minus 1. All right, so if we add those together first, we're going to get 15. Now, there's no way I'm going to get these bases to match. So since I can't get those bases to match, I can't use my little log properties. So what we're going to have to do instead is we're going to have to do the change of base formula, which we talked about earlier in our lesson. So that looks like this. Log base 10, top and bottom, and you put the 15 on the top and you put the 3 on the bottom. And this is a calculator problem. So to answer that, we need to get our calculator out. Room here. Let me make some room. Back in a minute. Okay, so we have log 15 divided by log of 3 equals 2.465. And it's going to be a good idea to round to about the thousandths place when you do this. So 2.465. Writing real quick. 2.465. What we got. So now I've got -3 times 2.465. And then once we're just going to keep working on our calculator then at this point because that's a weird number. So times a -3 minus 1. So it's -8.395. Now your final answer, go ahead and round that one to the 10th. So I'm just going to say it's -8.4. That's good enough. 8.4. The reason for that is because when you're graphing, you can't really be that precise anyway. But in the middle of your problems, you don't want to round too much because every time you round, you lose accuracy. But at the end, we're going to stick to the 10th place. All right, so there's that. So step 1, find your domain. Step 2, that tells you where your vertical asymptote is. Step 3, pick some x's from your domain. Make sure they're kind of spaced far apart. And plug them in so you can find the y's that go with it. Sometimes you get lucky. Sometimes you have to use the change of base form. But in any event, we're ready to plot everything and graph it. So that's step 4. So let's go ahead and do step 4. So my x-axis is going from -4 to +10. and my y-axis is going from -1 to -8.4. All right, now my vertical asymptote is what I'll graph first. It's at -5. And then I'm going to plot this point first. After that, -4, -1, so left 4, down 1 is a dot right about there. And then 10, comma, -4, 8.4 is, here's 10 down to -8.4 is going to put me like right about here. And you'd have to look at the notes that I wrote for you earlier, but basically you have to pick which shape of those log graphs that I drew would connect these dots and go against that asymptote, and it would have to be something that looks like this. Okay, and so that's that. I'll do both of these other ones for you. Both of them have a little something different here. The fact that this number in front of the x is negative is going to have an effect on our graph. And this is an ln problem, which is also a little bit different. So we'll show you both of those. Okay. So the only thing that's really different with this particular problem is in the very first step, and it has a visual effect at the end, but not anything mathematical really. So step 1, go ahead and let's find our argument. So we do 6 minus 6x needs to be greater than 0, minus the 6 on both sides. And as we talked about earlier, when you divide by a negative, you have to reverse your inequality. So that, notice the arrow here changed directions because I divided by a -6. So that means x is now less than 1. So as for step 2, that means my vertical asymptote is going to be at x equals 1, my invisible boundary line that I can't cross. Now the third thing I need to do is set up my table and start finding some x's that I'm going to plug in. So x has to be less than 1, right? So the first number I can think of is 0, so let's go ahead and do 0. And then we want to pick another number that's less than 1, but remember, we want it to be kind of far away from 0, so let's go ahead and just do 10 again, why not? Okay, and so now our job is to find the y's for both of those. So, show my work over here. Step 1, I'm going to go ahead and plug in 0. Save myself a little bit of work here. Now if I plug in 0 to this part, that's going to be 6 times 0, which just goes away, so I'm left with 6, right? And then from there, that's a change of base problem. You do log 6 divided by log 4, and our calculator is going to be our friend at this point. So, log 6 divided by log 4. .29, which we're just going to round to 1.3 at this point in the game. Okay, let's do the next one, plugging in 10. So if I were to plug in 10, oh, you know what? I'm sorry, I made a boo-boo here. You can't plug in 10. It has to be less than 1, right? So what I meant to write was -10. So that's my bad. Sorry about that. So if I were to plug in -10, you have -6 being multiplied by a -10, right? So double negatives makes a positive, so that's going to end up being a positive 60 now. And 60 plus 6 is going to be 66. And once again, we're just going to go ahead and do our change of base, so it's log 66 divided by log 4, and that will give us our final point that we needed. And that one's about 3. Okay, and so step 4, we're ready to graph once again. So my x-axis goes all the way to -10. and my vertical asymptote is at x equals 1. And my points that I'm going to graph are 0, 1.3. So probably like right about here. And then -10, +3, so like right about there. And we have to pick what shape would connect these dots and go flat against this asymptote. And it would be something that would look probably something like this. There we go. Now, so the reason I wanted to do this problem was because since there's a negative number multiplying the x here, that causes this inequality to flip. And the result of that is instead of my graph being on the right side, it actually ends up being on the left side. So something else to be aware of. All right, last problem. How do you deal with ln problems? Pretty much the same way. It's actually a little bit easier to tell you the truth. So in this case, what the argument is x. It's not x minus 8. If they don't have parentheses, then that means the parentheses go around the term right next to the ln. So my argument is x. So in this case, step 1, my argument x has to be greater than 0. There's nothing to solve for, so there's that. So x has to be greater than 0. And that means that my vertical asymptote is going to be at the imaginary line x equals 0. So for step 3, we're going to pick some numbers for x to plug in. We want to pick numbers greater than 0, like 1 and 10. And we're going to go ahead and plug them in and see what we can get. So ln of 1 minus 8 equals y. Now this we have a log rule for, right? ln of 1 is 0. So that's just -8. Okay. Next one we have 10. So if I plug in 10, I'm going to get ln of 10 minus 8. Now in this case, we don't really need to use a change of base because guess what? Our calculator has an ln button on there. It doesn't have a log base 4 button. It doesn't have a log base 3 button. It does have a log base 10 button, which is why we did the change of base. But it also has an ln button, so we don't need to do change of base. We can just punch this in our calculator just as you see it here. So I'm just going to type here, I'm going to put 10, and then I'm going to push ln. And that's 2.3. And then we just go ahead and do that subtraction there. 2.3 minus 8. Getting -5.7. So ln's actually a little bit easier because you don't need to use the change of base. You can just use your ln button calculator. All right, so we're ready to graph. Here we go. My x-axis goes all the way up to 10. My y-axis is going to go down to -8. Now my invisible imaginary vertical asymptote line is at x equals 0, right? And then my graph, it has the points 1, -8, and 10, -5.7. Like right about here, and the shape that would, the logarithmic shape that would correctly connect these points and go against this asymptote would look something like this. And there you guys have it. So that's the end of it. So now there's a lot there. Next week we'll have a little extra credit final, and that'll close us out for the year, guys. So talk to you later.